With that perspective, we took a simple techno-economic approach, and we said, what would it cost? How many wells would it take to build out a 50 or 100 or 250 megawatt power plant? And so we have those maps globally, and they're now published.
Welcome to Geothermal Unleashed, where we will explore the cutting edge of geothermal energy. I'm Elizabeth Cambre from the Vallourec New Energies team, and I'm here to help educate and document geothermal's rise in the global energy transition. I am pleased to welcome our guest today, Philip Ball, who is the director with Geothermal Energy Advisors. Today, we're going to talk about Philip's background in geothermal and what projects he's currently working on, as well as his involvement with Geothermal Radar. So welcome to the show, Philip. And why don't we get things kicked off by you introducing us and giving us a little background history on your career.
Good morning, Elizabeth, and thank you for having me on Geothermal Unleashed. My career, where should I start? I think post-PhD, I did my PhD in London, and I focused on continental breakup and the processes that evolved during rift initiation all the way through to seafloor spreading. And at that time, I was studying the Australian and Antarctic conjugate margins in collaboration with Geoscience Australia. Following my PhD, I took a postdoc in Norway, working with Professor Trond Torsvik at Geological Survey. And then that was actually a Statoil-sponsored postdoc, and very quickly Statoil sucked me into their organization. And I moved across to join the oil and gas industry from academia. So that's really where my career started out, principally as a professional. And I spent probably the next 18 years in oil and gas, really applying my PhD to oil and gas exploration, whereby I was looking at the how to model basically heat through time in order to understand the impact of heat and the deposition of sediments on top of source rocks, and how that impacts where and when we might find source rocks maturing and oil and gas migrating. So that was applied globally across different companies to help with the oil and gas exploration.
Okay, so you worked with Statoil, which is now Equinor.
Yeah.
Then you went to ConocoPhillips. You worked with ONGC, Saudi Arabia, and Total Energy. So you've worked all over the world. And so you're essentially, were you in the exploration team?
Yeah, so that's a good question. I've spent most of my career in what we call new ventures exploration. So looking for the new places to go explore, or looking for new places within existing basins, which have known oil and gas, but looking for the new plays. So if I was not in those teams, I was either in technology teams or I was in R&D teams. So I spent my career at the forefront of exploration.
So where are some of the exciting plays that you've actually helped to uncover around the world? Can you share any of those details?
I think some of the details I can share. I was very happy, very happy with some of the early work we did in Norway, integrating plate tectonics, integrating paleogeographies into sedimentary deposition, and looking at how the rift evolved through time. So you might imagine that all the faults are landward dipping, for example, but what we discovered is that that's not always the case, that you can have landward dipping faults, not just oceanward dipping faults, which is the kind of the textbook. So being able to decipher and unravel the sort of complicated geological histories that get overprinted through time, that allowed us to unlock some new plays across many margins around the world. Probably one of the most exciting that I worked on later in my career was with ConocoPhillips on the Angola margin. These were some of the first really deep water wells that were drilled, and we took all of our learnings, so my sort of accumulated learnings from the PhD, through the industry and the academic research at the time that was really leading a lot of the offshore exploration concepts, at least. We were able, in a way, to predict heat flow along the Angolan margin through time. Our results indicated that the company would not find oil as they were hoping. And unfortunately, they still went ahead and drilled 3 wells, which were very, very expensive. Verified our models, so we were very happy about that because we could predict the outcome. And what we learned from that was that while temperatures are cool present day, during the Sin Rift period, as you're thinning the crust and the lithosphere, we observe very, very high heat flows. And the indicators from the wells that we were able to study after the drilling confirmed our logic. And that logic was built upon observation from other rifts, such as the Red Sea, East Africa, for example. But also we would spend time in the Pyrenees, in the Alps, with Professor Gianretto Manachal at the University of Strasbourg, and we would go study what we could see in the nappes up in the Alps, whereby we could see exhumed mantle rocks with the sedimentary sequences on top. And by studying that, we could, reverse calculate what we thought was going on in Angola and other margins around the world. So that was, for me, this was really a very, very exciting time because we were applying field observations with results to very finite element models where we were predicting the heat flow through time and space.
Very interesting.
In conjunction with the deposition of sediments, with carbonates, with evaporites, and how that all complicates the signal, basically.
Yeah. Okay. So does that mean that with your experience of being able to find oil and gas reserves based off of heat mapping, I can call it heat mapping?
Yeah.
This is translated into geothermal then?
Yeah. So yeah, effectively, that's sort of how it happened, right? I've spent 18 years basically in my oil career mapping heat flow, mapping the crust, mapping the lithosphere. A lot of people would laugh at me because when I would approach a seismic line, I would look for the moho, I would look for the basement, I'd look for the seabed, and then I would infill the stratigraphy in between and the crustal structure in between, and in order to build up a picture of how that basin had formed through time. And that was a very different approach to most oil and gas professionals. And so that was how I had learned how to interrogate a basin. So how that applies to geothermal, of course, is kind of the same. Rather than trying to understand the last 200 million years of heat flow and where have hydrothermal systems convected, we're looking at that present day. So once I got in geothermal into my head, I started to think, well, it's a little bit easier than trying to map these systems back through 200 million years or more. And so how I got interested in geothermal initially, actually, I can pinpoint it almost directly to attending a conference in Jeddah in Saudi Arabia. Beg your pardon. I attended a conference in Jeddah in 2018. I think it was January or February. And I sat in on a session just out of curiosity about hot rocks. And it was a geothermal session, and a bunch of people had flown over from some of the labs in the USA to present to the Saudis on their findings. That intrigued me. There was a couple of talks there, ranging from drilling in Oregon, for example, at Newbury, to what was called closed loop at the time, which was not what we call closed loop today in the sense of ever technologies, but using an ORC or a binary system. So there was a guy presenting his work on exploration in Croatia using closed loop technology or ORC binary technology in a power plant sense. It was open loop in the subsurface, but he was pushing these new technologies, and so that caught my attention. And of course, as I had explained earlier, I've been mapping heat flow through time and space. Mapping heat flow present day seemed certainly a lot easier. And I started thinking, if there's technologies out there that allow us to drill into hot rocks, why are we not doing more of this? And it sort of became an obsession after that, because I couldn't understand, heat is ubiquitous, it's everywhere. And so also from our oil and gas exploration, for example, at that time I was working in Saudi Arabia in the Red Sea. Aramco had drilled wells in the central Red Sea that had melted the Schlumberger drill bits because of the high heat flow. They'd also followed up wells in the northern Red Sea that at 6 kilometers below sea level, we'd hit potable water at, very low temperature. And then 15 kilometers to the west, we'd hit hypersaline waters that had seen paleo temperatures of 240 degrees C based off the geochemistry that we did to understand, the evolution of those fluids. So within one basin, we'd seen, low temperature waters that were potable. And then 15 kilometers west, we'd seen waters that were hypersaline and had seen 240 degrees C. So we started to see a picture of a basin, a graben, having highly segmented hydrothermal systems in them. And so that interested me because that variability was fascinating, and it also fitted into my background of understanding how heat flow evolves through time, because we can go to the Alps and we can go look at paleo hydrothermal systems, for example. And those hydrothermal systems in rifted margins are part of the process of cooling down the rift as you've perturbed the geotherms due to the extension and the thinning. And
So would you,
so
can I ask a question? When you're doing heat mapping and like if we're looking at conventional versus next gen, does it matter? I mean, are there expressions at the surface? Does that impact?
it's a very good question. So I think crudely simplifying things, exploration has sort of followed the hot springs approach of this is my show at the surface. There's hot water down below, and we've drilled into those. But that exploration methodology has not really been that successful. Historically, obviously, we have a geothermal industry in the conventional sense. Companies like Zanskar are really interesting, and also Ormat have proven a lot of success chasing what's sort of termed blind geothermal today.
Yeah.
And so obviously there is no surface expression, and that then relies on indirect methods to understand and map the occurrence of that hydrothermal anomaly. So this is sort of where my background comes in. And I guess we can talk a bit about the work I did at CATF in that capacity. We sought out, there is only 53 wells globally that I've found that have drilled into rocks at 350 degrees C or hotter. And so we built that database up. But that's not enough to constrain any kind of exploration model globally. So we approached JC Afonso at the University of Twente in the Netherlands, and he'd built a model in 2018 called LithoRef. And it's a lithosphere reference model. And what we did was we talked to him and said, could we turn this thermomechanical model of the lithosphere into a heat flow predictor? And that's basically what we did. And so the value of that is it's a physics-based model of the lithosphere, and it looks at the conductive heat from the lithosphere up into the crust. So because there's a limited number of wells, this provides us a bottom-up approach, basically, rather than a top-down approach with your wells to predicting heat flow in the subsurface. And it's relatively robust. I mean, it's not perfect. Right now, it's at low resolution, and we're looking to improve that resolution with bringing in new data sets and increasing the confidence in our modeling. So that work actually just got published February 17th, I believe, in a book called geothermal engineering.
And okay, so what you published is the data on you. It's called a lithosphere.
So the model is based off lithoref. So it's a very
Lithoref. Okay.
reference model of the Earth, and
Okay.
use that model to calculate the depth to the conductive
Got
isosphere.
it. And so, okay, so that was published.
Yeah.
But then you said you were mapping geothermal resources with Clean Air Task Force. Did you map like the entire globe?
Yes, we did. Yeah. So it's a global
Okay.
model. And so with that perspective, we took a simple techno-economic approach and we said, what would it cost? How many wells would it take to build out a 50 or 100 or 250 megawatt power plant? And so we have those maps globally, and they're now published. So
Okay, wonderful. So, and then on those maps, I'm assuming super hot rock is included in that. And I'm very eager to hear what is your take on super hot rock?
yes, it is. So that particular publication is designed at emphasizing the sort of running room that superhot rock has. Where is it shallowest? Where might it be most economically targeted? The paper focuses less on the economics, but more on the geodynamics. So where is the heat? Why is the heat there? We try and understand that from a from a sort of geological perspective of, is all the heat located in the basin and range, which is an extension or province in the USA, or is it located in back arc basins or orogenic systems, which is where the plates collide and you form a mountain belt. And so we characterized that. We characterized each geodynamic domain based on how much shallow heat is present. And what we found was actually interesting. It wasn't what I expected prior to doing the analyses. And the USA is very, very blessed by the basin and range, which has a very unique geological condition in the western part of the US, whereby we formed through orogenesis a mountain belt, and then that mountain belt has collapsed. And we go through what's called a wide rift setting, and that is what we call the basin and range. And so it's extensional today. It has very, very high heat flows. It has a very, very thin lithosphere. And that's an anomaly. And based on a geodynamic classification, we don't see that all basin and range provinces around the world have the same heat flow. And so that, for me, that's a fundamental question. We need to understand, is that an error in mapping a basin and range province, or wide rift as they get called? And in order to improve our ability to explore, we need to understand that variance. Why they are not all the same. Because if it's classified as a geodynamic province, it should have similar properties. And what we observed was that wasn't the case. And we observed that across every single geodynamic province. So the structural variability within provinces needs to be understood. And for me, that was a surprise, to be fair.
Yeah. Okay, so you've done a lot of mapping, so you know a lot of things. And one thing I'm always interested or kind of looking at is when you look at these other, you can add geothermal to other value add. I don't even know if you would call it value add. It could be the reason you're doing geothermal, but when you look at lithium or you look at other critical minerals or critical fluids, have you mapped out where there are potential intersections between these?
That's a really good question. Not yet, I think is the short answer. It's I probably try to keep myself a holistic geoscientist. I try not to become too specialized in any one
Sure.
particular area, but keeping that holistic view, of course, there will be synergies, there will be overlaps.
Yeah.
I haven't yet got that far to understand it, but it's a really key question, and it's something I ask myself all the time, because I'm going to talk a little bit about the Red Sea.
Okay.
Some of the work we did when I got to the Red Sea, um, I was very, very interested in, well, there's a big debate in the Red Sea. Has it gone to seafloor spreading or hasn't it? Did that extension process lead to mantle exhumation or not? And there are, dozens of models and dozens of opinions. And so we tried to kind of disregard all the noise and just look at the data. And unfortunately, a lot of the final results are confidential. Aramco wouldn't release them, but we conducted chemostratigraphy on all of the deep wells that went into basement. So, and what we were looking for in that process was markers. So when you exhume mantle, that process of hydration of the peridotite releases certain minerals, chromite, nickel, and others, for example. I just focus on those two. Chromium and nickel are key. So if you have exhumed those rocks, you should see a chemical change in the water, and those metals get precipitated into the stratigraphy, and they should form a marker. So we were looking for those. We actually published a poster presentation on that at EGU in 2017. And what we found in the very simple work that we were able to publish was that we had Mississippi Valley type deposits, nickel and lead in certain places along the margin. And we saw other markers. we couldn't answer the question at the time. Had we gone through mantle exhumation? We saw mantle. We believed we saw mantle exhumation on the seismic, but anyway, I'll try and cut the story short. Basically, what I think is that there's an awful lot of synergies between our understanding of how rifts evolve, how rift architecture then controls the orogenic process when you then collide continents back together again, and that will also impact significantly the occurrence of energy critical metals as you collide and warm things up. Things are going to move around in the fluids and then reprecipitate in different areas. And so understanding the rift architecture, understanding how that controls the orogenesis is going to impact a lot of the mineral distribution through time. And so whether that's lithium, whether that's hydrogen, whether that's cobalt, nickel, lead, zinc, I personally believe that we need to somehow be able to unravel the different tectonic episodes and then get back to where did those minerals originate from before they remobilized into their present day position.
Yeah.
So I think there's a massive synergy.
Yeah, no, it's for me, I find this whole subject to be quite fascinating. Okay, let's turn to talk about geothermal radar. So you seem to have a really good understanding of geothermal plays, which is the foundation, right, of geothermal radar. Can you talk about your involvement and the startup? And I'll just add that geothermal radar presented at the Geothermal Rising Texla Oak Rig. We called it the Geothermal Groundbreakers, the launch pad, and they did such a fabulous job. Big kudos to Geothermal Radar for their presentation. But can you talk a little bit about geothermal radar?
Yeah, thank you. So I met Vladimir Stroganov, probably let's say 18 months ago, and he was building a global model with a techno-economic calculator attached to it. That sort of coincided as I was wrapping up my CATF experience, whereby we had maps, but we were looking for ways to be able to drop a pin at any location and calculate the techno-economics. So as I left CATF, it seemed like a great relationship to develop with Vladimir, not just because of the work that we had published at CATF on the super hot rock maps, but also because I've been very diligent over the years in terms of archiving data sets that are in the public domain relating to heat flow, because that's basically been my job.
Yeah.
And what we've built at Geothermal Radar, I was the data guy, and the geoscience guy, Vladimir, is the analyst and the numerical modeling guy. And so that relationship was really perfect because I had the data, but I didn't have the techno-economics. He had the techno-economics, but not the data. So we've ended up building a surface to lithosphere thermal model. So that's building on all of my career, basically, whereby I've been interested in the lithosphere, in the mantle, in the crustal thickness, in its lithology, and how all of that impacts heat flow. So we're building that into geothermal radar to have a global model from surface to LAB, as we call it, lithosphere asthenosphere boundary. It's approximately the 1300 degree isotherm. And so from that, then we can input all of our different data sets, geophysical data sets, structural data sets. We use that to cross-validate because there should not be a heat anomaly that we don't know about. It should correlate with a thinning event, or it should correlate with a magmatic event. And so we build in basically a global model now with uncertainties factored in, we can predict the depth to temperature. You can look at that if you want. So Vladimir is very clever. He's taken my data and he's sort of using, I guess, machine learning approaches. So we can take the data and then we can extrapolate and say at 5 kilometers, what is the temperature? Or we can say, where is it 400 degrees C? And then produce a map of depth to 400 degrees C and produce isotherm. So that then calculates gradients, and we also then have uncertainties to temperature. So how we're using that is because we now have a holistic global model, it's as good as the data in, but we're always looking to improve that. But right now, we can tell you at any point in the world what we believe the gradients to be and what we believe the uncertainty on those gradients are. And so we feed that into the techno-economic models and then look at ways as we're prospecting, as we bring that into a project, how can we then reduce the uncertainty on the existing data sets that are out there? And that approach, I hope, is going to be of interest to people for reducing the uncertainty in their exploration. And one of the key things that I bring to it from the Geothermal Energy Advisors aspect is we look at bringing really the oil and gas processes into geothermal. So probabilistic modeling is important rather than deterministic modeling of a resource because you want to know what the uncertainties are.
Sure.
And similarly, we started talking internally, at least, about a GRMS, so a geothermal resource management. So like they have in oil and gas, we have a petroleum resource management. And so we're looking at, can we define the resource and can we turn that into a reserve? So we're building the workflows and the concepts of, okay, we have the heat maps, we have uncertainty, we can map a target, we can choose how we want to engineer that project. Does it want to be closed loop or open loop, or is it actually conventional? And then we can then attach the economics to that through the lifetime scenario.
So who uses this software? Is it investors or is it geothermal startups? Is it universities?
Yeah. That's a really good question. So we've been talking, for example, to the UK government. They're not currently users, but we have been talking to them about giving them license. We've been approached by a nonprofit, in California, who want to better define and understand their geothermal resources, and so we will give them geothermal radar, give them access to it so that they can look at that. Through my relationship at Keele University in the UK, where actually nearly it's 25 this year. So 8 years I've been an honorary researcher there. That's my way of giving back to the university that trained me. I have very fond memories of my undergraduate years. They were very formative for me, and I have always maintained a relationship with the university. Um, so we're giving the code to the university to
Oh,
allow
wow.
students to work on it, and also allowing them to uh, learn how to run the software. And that's a great way for us to not only get feedback on how does it work,
Sure.
but also hopefully refine the products and refine the outputs. Um, so yes, we're open to sharing it with universities in a sort of limited way, but also with governments and government bodies and nonprofits.
But then your market is geothermal
Oh yes,
completion.
to answer that part of your question,
Yeah.
right now we've been working with a major oil and gas company,
Okay.
which
Fabulous.
was not the bias. We were already interested in taking the oil and gas process because myself and my other colleagues in Geothermal Energy Advisors have an oil and gas background, so we have that methodological approach that we wanted to take from oil and apply to geothermal, and that was really a perfect alignment. So we've worked with a major oil and gas company, and we're working with currently with a couple of startups.
That's wonderful. Well, Philip, we are about out of time. We had a fabulous discussion today, and I
Yeah.
want to thank you so much for joining me on this episode of Geothermal Unleashed. And I hope to our listeners, today's discussion has sparked new insights and deepened your understanding of the geothermal industry's incredible potential. Until next time, keep pushing the boundaries of what's possible, and let's continue working to unleash the full potential of geothermal.
Thank you, Elizabeth. Thanks
Thank
for your
you.
questions.